We are Team 19, and in the past few months, we have been working in collaboration with Team 20 on our application UCL Open Illumiroom version 3, which gives anybody the ability to create and experience expanded media. Our application runs on any Windows device and offers a wide range of projection modes, including user generated effects, which are displayed around the user screen using a projector, creating a larger and more immersive display. These high quality graphics are based on intelligent processing of the audio and video feed from the user's device. To give you some background, our project is an attempt at remastering the original Microsoft Researchers Illumiroom proof of concept from 2013. UCL Open Illumiroom version 2 from last year achieved calibration and introduced 9 projection modes in their Microsoft Store deployable. We developed on version 2's codebase with a focus on adding extensibility and automation.
So before jumping into the technical requirements, we first thought about the main problems that this project will tackle and what the ultimate goals of this technology are. In gaming and entertainment today, we're limited to the confines of our screens, which caps our sense of being in the game or part of the action. Current augmented reality setups don't help much unless we've got the right space. A big empty wall isn't something that everyone has. So our project sets out to do two things. First, create an immersive experience that goes beyond the screen, blending games or movies within the room that you're in, no matter its size or shape. And second, to make this technology adaptable to different spaces without a complicated setup process. So our system should not only be immersive and adaptable, but also accessible and compatible with the tech and spaces we already have, including in hospitals, making stays there a bit more bearable. So now let's take a look at how we're planning to achieve this. To bring Illumiroom V3 to life, we had to set our priorities, and so this resulted in the following key requirements. Our system must perform real-time analysis of the display and use different techniques for intelligently deciding which shaders to deploy, ensuring that the experience is always in sync with what's happening on the screen. Our solution must not have a one-size-fits-all rendering, but instead have various projection modes. These range from modes that react dynamically to game environments to those that enhance the ambience for movies or even just your living spaces. And to put the power of this technology right at anyone's fingertips, our system must present an intuitive user interface, which is the key to personalizing your experience or the user's is by selecting settings and switching projection modes with ease. And finally, the whole point is to deliver a Microsoft Store-ready application that's both robust and user-friendly, underpinned by a versatile Python backend.
Now, as part of our goal to move away from hard-coded effects, we went through a thorough testing phase with various graphics libraries. We tried both Python and C++ versions of OpenGL, a popular graphics API, but we realized the learning curve was too steep for us. DirectX is a popular Windows graphics library, but despite our best efforts, we could not get it running on our systems. Using Pygame, we were successful in implementing various effects such as lightning and snow, but it would have been difficult to integrate it with our existing application since it wouldn't allow us to manipulate individual frames. OpenCV, the library being used in version 2, can be used for simple effects like our particle effect, but is unusable for complex graphics and was only used by us for utility needs. A primary issue with these four libraries was that they made it difficult to enable user generated effects. Our solution for these problems was using GIF based effects and using tkinter and pillow libraries to manipulate frames. Lastly, we also tried developing an effect that displays words spoken by the user on the screen using OpenAI's Whisper model. However, we could not make the rendering and audio capture asynchronous.
So this is the system architecture diagram. The main Open Illumiroom MFC UI serves as the primary interface. The user interacts with this GUI to control the system's functionality. To create a custom background effect, the user can launch the Create Shader UI from the MFC and make his own shader. The shader UI saves the background effect and then writes the information to the JSON files. The Python backend script is the core processing engine. It reads the JSON settings and renders the background effects using the triggers created by Team 20. The Python backend uses AI to process the activity on the screen and then renders a suitable effect. This structured data flow maintains separation of concerns while allowing flexible customization through the JSON configuration files. So we have used Python, C++, and machine learning frameworks like TensorFlow and scikit-learn for this project. Python served as the backbone, managing backend operations, machine learning models, and the shader development with OpenCV and tkinter. C++ with MFC was used to develop the frontend. It writes all inputs by the user to JSON files, which is used by the backend to process and render shaders. We have also used TensorFlow and scikit-learn for implementing advanced machine learning features, notably a convolutional neural network model for weather detection trained using TensorFlow's Keras. It dynamically adjusted the shaders based on the weather conditions in a game or movie that is playing on the screen. Our main deliverable was the development of an MFC-based executable application ensuring seamless operation of the Open Illumiroom v3. This application writes user inputs to JSON files and makes it easy to integrate with the existing systems. Our achievements include providing users with a platform to create custom shaders and configure the triggers effortlessly. Additionally, we implemented an AI algorithm to auto-render shaders based on the screen activity, enhancing the immersive experience. Furthermore, we have optimized our program to run efficiently on older computers, ensuring accessibility for a wide range of users. For example, people with mobility issues in hospital wards.
We will now show a demonstration of the various effects and experiences that we offer. This custom experience triggers a switch from the default particle effect to the anime effect based on a specific timestamp that is provided by us.
So now we have AI projection mode for games. So in Rocket League, when the ball is still in play, the blur effect is displayed in the background. And as soon as the user scores a goal, the program will use AI to read the score text on the screen and display a celebration shader in the background. In Forza, the backend uses AI to read the speed of the car from the speedometer, and when the speed of the car is greater than 70 kilometers per hour, the speed effect is rendered. Otherwise, we just blur the background.
Okay, so for the AI weather projection mode, here you can see Minecraft during a rainy day and notice how our background effect mirrors the raindrops. As we transition to a snowy scene, our system intelligently adapts, introducing a snowfall effect in the background. And as we return to rain, our background synchronizes to display a matching rain shader, maintaining the continuity and depth of the visual experience. The way the system works is through the use of a neural network was trained with pictures representing various weather conditions, and thus it manages to adapt dynamically.
This mode automatically detects the change in color on the screen based on what the dominant color is, using a clustering algorithm. Here we are switching between the rain, night, snow, and fire effects corresponding to the blue, black, white, and red colors, as you can see. The mapping between the colors and effects is also completely customizable, and the color range itself can be modified by just going to the JSON files and changing the pixel values.
So this is the shader creator UI that we have, and the user is able to select a GIF that has been made, and you can select any GIF. I'm selecting the rain GIF here that I've downloaded from the internet, and you can name your shader. So I'm gonna name it rain test, and once you click submit, this is going to stitch that GIF onto the background image that we have for the projector, and it's going to take a few seconds here, but once that's done, we should be able to have a final GIF. And as you can see, this is our final GIF that has stitched the rain onto the background image. Thank you.
And special thanks to everyone from the computer science department that has helped us throughout the development of this project. Our progress wouldn't have been possible without your support, so thank you very much.